Hello everyone. Yeah, it's been a while, and today I would like to continue to show the analysis using Slide software to analyze the solvability. And Slide software is one of the application of the rock science software, which is the software that used to model and analyze the stability of the slope, tunnel, or any application of the geotechnical engineering. And today we have the slope stability analysis exercise, and we focus on the embankment dam, the stability analysis, its slope, the embankment slope. And we can see that in our uh, dam, we have the downhill slope, we have the uh, uphill slope, we have the foundation of it, and in this stage we already draw the external boundary, which is the whole dam boundary, and also we already draw the material boundary, which is the boundary, internal boundary that divide each component of the dam, such as we have the concrete layer at the upstream, we have the filter transition, we have the impervious layer at the upstream boundary, we have the foundation of the dam, and we also have like the the core, the inclined core of the dam as well. And in this stage, we already compute the means we already assign the material in each component, the foundation of the rock, or the core, the the filter, impervious layer, and also the concrete layer. So we skip the part that we define the material property and assign it to our exercise, our boundary, our dam, and we continue to show the how it's analyzed and the result look like. So in this exercise, we have the limitation of the our exercise, such as that we only focus on the limit equilibrium analysis, LEM, limit equilibrium method. We also only focus on the dry condition. It's mean that this we can consider at the end construction state of the dam. It's mean that there is no water at the upstream yet. So at this stage, we already assign the material I mentioned, and we assign the property of the material as well. So to continue, we want to draw this slip surface. Slip surface is the surface that define the slip failure phase of the each slope. So if you want to analyze at the upstream slope or analyze at the downstream slope, we have to be careful about the setting like this. We want to set the failure direction. If you want to focus on the downstream slope, you can put the left to right. If you want to focus on the upstream slope, you can click on the right to left. If you don't click on it properly, it will not generating the result. So I want to start from the downstream slope. So it's left to right, it's correct. So after that, we want to draw the grid. This is the uh, how we define the slip surface. So I just do the just add the grid randomly, just like this. So it's, yeah, 22 and 18 of the interval in each direction. So I just start as this example, and then we just continue compute it. Yeah, just save it or something, and then after that we already computed, we computing it, and it's maybe taking a while. And you see the progress detail right here. You can see, and it's the each method of the slip surface. So you can decide which method you prefer to analyze. And for me myself, I use Bishop method, generalized limit equilibrium method, Spencer, and Janbu. So you can select the other as well. Okay, after computing this modeling, and we can see the result in the interpret. So we start doing interpreting. Yeah, this is how the result look like. It's mean that this one, when it's the default of the software that it show the value in here, this is the critical one. It's mean the minimum one. So here the minimum slip failure, the minimum slip failure surface, and also the minimum factor of safety of the slope. So it will be fail with its minimum safety factor of 4.177. So in here, this is the result of the Bishop simplify method. So after we do four different methods of the subsurface, and we can see in each method, just click on it to see. So it's mean that in the Janbu, so the minimum one is lower than the Bishop. Just in this case, it's not applied for all the exercise. So in here, Janbu simplify is have the it has the minimum factor of the 3.801, and for the Spencer, yeah, it's quite similar or close to the Bishop, and also the Morgenstern or the generalized limit equilibrium is equal to Spencer, just for this case. So this is how the result look like. So, and also we can see the whole, how the subsurface of all the subsurface. So it will be like that. Like this.